Okay, if I gave you, I say that and then I go do something else. That's the way. That's the way a lot of sciences are. Not really linear. If I said, what's the oxidation number of platinum in this compound?
Are you saying that, or are you?
Yeah, I'm saying it. If I give you, go ahead, Jules.
+4.
+4. What's chlorine?
-1.
There you go. What if I give you
+6.
nitrogen's +6, oxygen's 2-. And Jules, you're out. What if I give you
The P
oxygen's 2-, good.
+3.
All right, so we got oxidation numbers. So all that we're gonna do is use those oxidation states to track electrons as they move from reactant side to product side. So we're gonna call that balancing the half reactions. Remember, the half reactions in these redox equations are what happens to the one species on one side and then on the other, all right? So we're gonna follow the metal from one side to the other. We're gonna write 2 half reactions. We're gonna balance all elements except oxygen and hydrogen. We're gonna then balance the oxygens by adding waters. We're then gonna balance the hydrogens by adding H's. We're gonna balance charge, which is just as important because we're chasing the electrons across the reaction. Then we're gonna add electrons on both sides of half reactions, and if necessary, you're gonna multiply 1 half reaction by a whole number coefficient so that we get equal numbers of electrons on both sides, and then we can subtract them out of the equation. Add the 2 half reactions, cancel out any E's and any species that appear on both sides of the equation. So, did we do? Yeah. So there's an extra step if we're basing. Usually is. Balance redox reactions in acid first, which is by adding the H+ and waters. When enough OHs and H's appear on one side, combine to make H2Os. Cancel out any redundant H2Os. So that's the game. We balance an acid, we don't have to worry about adding OHs to equal H's. Because in acid, we have extra H's. In base, we have extra OHs. So generally, you're gonna know that you're basic because it's gonna have a hydroxide in it. So, 10 steps, sometimes only 7. So write the balanced redox reaction for the equation dichromate ion and copper 1 to give chromium 3 and copper 2. So step 1, write the half reactions. Chromium 2O7 dichromate, right? Chromium 2O7, 2- goes to chromium 3. Copper goes from +1 to +2. So which one's oxidized? I can talk about pot again if you want.
Yeah, copper.
No.
Yeah, copper, right? Because copper lost an electron, lose electron oxidized, going from a lower oxidation state to a higher oxidation state. That means that just by the definition of the equation, right, the other one's reduced. So if chromium goes to 3, what was it when it was Cr2O7? Oxygen's -2, right? There's 7 of them, that's -14. We have to have 2 left over, that's -12. And then you divide that by 2, right?
-6.
Yeah. Well, what? Yeah. +6, right? Is that right? Did I do that right? -14 and +12, 12 to make a -2, so 6 over so chromium 6 to chromium 3. So that's the reduction. So, and that works out, right? So how do we balance that, steps 2 through 5? So we have 7 oxygens on this side, and to balance it out, we add what? Waters. So we have 7 waters. Right. Now we have 14 H's on this side, so we add 14 H's on that side. And the difference in electrons is 6. How do we know that? Emmanuel, how do we know that the difference is 6 electrons? Let's say for sure we know the difference. What do we know for sure going from chromium 6 to chromium 3? How many electrons did we add? Still you, Emmanuel.
3.
Yeah. So if we do that twice, we have 6. Okay. Let's look at the other one. Copper plus goes to copper 2 plus. And remember that when we lose electrons and we're oxidized, it goes on the product side because we've released an electron. The electron that was here is now a free floating free agent. Right? It's in solution. Okay, so when we are reducing, we have to add an electron to go from +6 to +3. Right, we have to add 3 electrons, and we have to do it twice. So, all right, so now those are our 2 half reactions. But we have to make the reactions equal, right? You have to do 6 times the copper to get 6 electrons, right? So now you do it, you balance it out, and you're left with this equation. Is that long enough? You guys got it? Alex, you good? You know, I'm really glad. I'm going to say this about you guys because I said some harsh stuff at the beginning. I really want to say that this late in the semester, it's great to see so many people in here. I'm really happy with the turnout. I hope that most of you know what's going on. If you don't, find resources. You got these 2 here. I'll be here Friday mornings as well. I'm here an hour, at least an hour before class most of the time, sometimes 2, sometimes only 45 minutes. Talk to me, communicate, don't just disappear, okay? Like we're so used to just, oh, this is too much, I'm done. But you're already here, you're still here, we're almost done. So, right, and the farther you get in this, the more likely that if you don't pass it this time, you'll pass it next time. So, I want to encourage you to continue showing up. And you never know about me, I could do something crazy. I did it during COVID, right? So, I mean, to help you. I don't mean like I'm gonna all of a sudden do something crazy, like.
Just stay alive.
I'm trying, really trying to stay alive. Me and John Travolta, Saturday Night Fever, all about it. Right? You got it. All right. So, and that wasn't, I can't really do it because it just, white pants. I had to wear those angel flights back in the day when people were doing a lot of this. In restaurants, we had these pants called angel flights, and they were super tight, and then they bell bottomed at the bottom.
Oh my God, I need to see a picture.
And you know what? You know why bell bottoms exist, right? Because that's where people kept their weed, right? They would. It went like this, and then you put it in your sock, carry your baggie around. Not me, because I didn't do that kind of stuff because I'm a good boy.
Would you mind going back and explaining step 5 again, the balancing the electron?
Perfect. Thank you, Jules. Let's go. Step 5, balance charge by adding E minuses. Okay? So what we have here, right here, So let's look at step one. Step one says we have dichromate going from chromate +6 to chromate +3. How do we get there? We have to add electrons. So to go from +6 to +3 one time would be 3 electrons. Yes? And because we're reducing something, we have to add the electrons on the reactant side. Okay? So when we're looking at this, right? When we look at the half reaction, we only have chromium and chromium 6 and chromium 3. So we're going to cover all those steps, Jules. Chromium 6 to chromium 3. There's oxygen on this side, but we can't just add oxygen on the other side. The only way we can add oxygen is to add water. So we add as many waters as there are oxygens, and there's 7 oxygens. So
Why is chromium? Oh, because it's chromium 3. Is that why? And there's 2.
right. So
Why
it's
is it chromium 6?
that's why we're doing this part over there. But hold on. And oh wait, I have this board. I forget. Hello. I have. Hello. Yeah, lucky you. Chromium. Right? So 2 minus 1, 2, 3, 4. Look, some of these even look like 2s. 2, 4, 6, 8, 10. I don't even know. 14. All right. But we need 2 minus there, so let's cut one of those off. That makes this minus 12. To balance it out, this has to be plus 12, right? There are 2 chromiums, and you have a plus 12 charge, so each chromium is plus 6. Yeah? Yeah. Okay.
Yeah.
Right. And so that's where we have to get used to being able to distribute that charge. All right. So we go 14 hydrogens on one side because we added the waters, so now we have to put 14 hydrogens here because there were no hydrogens there. Right. Now, how do we get from chromium 6 to chromium 3? Well, if we have chromium 6, right, chromium 6 is missing how many electrons? It has, what is chromium, 24? What is chromium 24 in your periodic table?
24.
How did he know that? Back in my day, we had to memorize this stupid thing, and I barely remember any of them. 24, right, which means we have 24 protons, but we're plus 6, so we only have 18 electrons. Chromium 3 still has 24 protons because if you change the number of protons, you change the element. So, but plus 3 means we only have 21 electrons, right? So in order to get from 24 to 21, we have to add 3 electrons. Yeah? Does that make sense? And since we have 2 of them, the second chromium 6 that goes to chromium 3 plus needs 3 electrons. So 3 electrons twice.
Man, it's a lot. Are there faster, like, I mean, find out in the faster, like, I just didn't know why it was, chromium 6 until I read the actual directions.
Okay, tell here.
Yeah.
Yeah, so you have to pull out the oxidation state yourself.
Mm-hmm.
Okay. You guys with me?
Yes. Yeah.
And you see where, so now, once we get the 6E's here, we have to balance that, right? We can't just make up electrons and let them go, right? It's part of our conservation of mass, conservation of matter. So we track those electrons. In order for this reaction to take place, we have to be electronically balanced as well. We have to keep track of our electrons. So that's why in step 6, we multiply by 6 so that we have the same number of electrons on each side of the equation. So we're balanced out. We had 6 on the reactant side, now we have 6 on the product side. So we have to do this 6 times. And so when we do that and add it all together, now we have 6Cu plus, 6Cu2 plus, so our electrons are balanced. We used 6 electrons to take chromium from 6 to 3. We lost 6 electrons to take copper from +1 to +2. 6 and 6. Does that work, Jules?
Why do you have to times it out? Why can't you just throw the 6 on there? Cause you're not really multiplying it by anything. Or
Yes,
are
you really are.
Where? Show me, point at it.
We're in Missouri now, it's the show me state,
Show me.
which is, you know, that's in somewhere in between California, New York, maybe, I don't know. Somewhere between the two. So if I have this, right, oops, do some dancing, right? There's only one electron here, so if I just make this 6 electrons, where did that electron come from? Where do those 6 electrons come from? You can only get 1 electron per CU, so there has to be 6 to get 6. That means they make 6.
No, I know that, but why can't you just throw the 6 on in front of all the CUs? Like, you're above the.
Because those coefficients are 1, so if they were 2, you can't just switch it to 6, you'd have to multiply it by that
Okay,
as well.
thank you. Okay.
Get up here, Kylie. I'm gonna sit over there. Let's see what's going on in this class, because I have no idea. All right.
Okay. So
Does that
you
make
do,
sense?
you do actually have to times them.
Yes.
It's just in this case, it's by itself.
Yes.
Just nod my head and say yes. Okay.
Okay.
All right. So now we're gonna do one in basic solution. So the same thing, only now we have a couple extra steps, the other 3 steps at the end. So
Okay.
we're gonna write the balanced equation for permanganate again. And permanganate goes from, what is permanganate in this one? What is the manganese in this one?
Yeah, +7.
Mm-hmm. Who said that? I'm gonna have to put it. It's good though. At least somebody's speaking out. Thank you, Patty. I don't wanna say anything, but I'm like on a 3-day streak with you.
You didn't
Sure.
want your credit points. Waiting for 'em.
What is it?
Well, you don't get any now. You say stuff like that. That's what makes it whimsical. I put them down when I want to. Okay, so permanganate. If you guys don't get manganese is +7 on a test, when I say what's the oxidation state of permanganate, you weren't paying attention because we've done permanganate a bunch of times. It's always +7,
No problem.
right? Once you've determined it, it stays the same. Every time you see nitrate, it's +5. Nitrogen's +5. Every time you see permanganate, Mn's +7. Every time you see dichromate, chromium's +6. All right. So the half reaction then is MnO4 goes to Mn2+. Iron goes from 2+ to 3+, so iron is oxidized. That means manganese is reduced. Why? Because we keep track of the electrons. If one gets reduced, something has to lose electrons. That's the beauty of oxidation reduction. So the first step, there's 4 oxygens, so we have to add 4 waters. That makes sense,
Okay.
right? And then since we added 4 waters, now we have to add 8 hydrogens. Right? Now, we go from manganese 7 to manganese 2. That means we have to add 5 electrons to go from 7 to 2, right?
Yeah.
Yeah, yeah.
Okay. So I wanted more than one head shake. And head shakes are good, I see them, but I like a little verbal confirmation as well.
Got it.
Because everyone has beautiful voices, and the sound of on a clear day, you can see forever. Okay, iron 2+ goes to iron 3+, so 1 electron. So I already know we're gonna have to multiply this by 5, right? To get to 5 electrons. So there have to be 5 irons. You have to have 5 iron molecules to give you 5 electrons to balance out the manganese. So we'll make those numbers equal and simplify. Right, those are my 5 times. All right. But that would be an acid. So now there's the extra thing, we have to neutralize the protons. What does that mean? That means just take out the H plus. Right. For every H plus, you have to add 8 OHs. Anywhere we can make water, you do. So 8 H plus, 8 waters, leaves 8 OHs, okay? And then we finish. And then we have 8 H2O plus 5 Fe2 plus M yields Mn2 plus 5 Fe3 minus plus 4 H2O plus 8 OH.
Can you go back to step 6 and 7, please?
Okay. Yeah, these are, you should have this slide. These slide. No?
You're not done, like you have, I have it.
Oh. Right, I didn't print out those pages, I'm sorry. That's it. I printed out the last 4 pages. All right, so we good from there? And go on. Again, let's do that again. So, when we're doing acids, right, we can stop right here. Because anything that's done in acid is gonna have excess protons in solution. Remember, this is all happening in solution. We have ions in solution, we have water in there, but this is what we're doing with the actual ions that are in solution. Yeah,
Oh, I can't remember, but you know it's an acid when it says in basic solution, so that's how you know you have to do that next step?
Yeah, if it says, because it'll either say in acid solution or in basic solution. So in acid solution, that's when we do this part. But we also do this part in basic solution, and then we say, okay, we're gonna take away all the H plus. And how do we do that? By adding, because we have excess OH minus. Right, we have excess base. So part of acid-base chemistry is the neutral part is equal concentrations of H plus and OH minus, which gives us water. That's why we call it a neutralization, because the amount of H plus equals the amount of OH minus. Now, if it's an acidic solution, then the amount or concentration or moles per liter of acid is greater than the moles per liter of base. If it's basic, then the OH dominates and the concentration of moles per liter of OH is greater than the concentration of H plus. Okay, and if it's neutral, then we have water. So what happens is, now we have this H plus in here in acidic solution. Now we're gonna make the solution basic. So we're gonna have excess OH. So that's gonna use up all this H plus and make waters. Okay, so that's the next step, right? We have H plus. We're gonna add 8 OH minus, because we have plenty of OH minus. We have an excess of OH minus. We have an excess of hydroxide. So we're gonna neutralize out all those protons, make water out of them, that's what we do. But we have to keep track of how many there were. So there were 8. And we bring that down, so 8H plus 8 OH minus neutralizes, making water, makes 8 waters. But there's nothing to neutralize this base on the product side. So we're gonna have base in the product side, because it's in basic solution. So that means there's extra hydroxides floating around in that solution, and there are 8 of them. And we just add that to our already existing equation. Then we make our waters, and what happened? There were 4 on this side, 8 on that side, so there's 4 left over.
What?
Right? Because here's 4, when we did it in, let's go back.
No, I mean, okay.
So remember, in order to balance this, we had 4 oxygens. In order to balance oxygen, we have to add water. So we added 4 waters to the product side.
Okay.
Then we had to add 8 H's to balance the waters to the reactant side. But because we're in base, now we have to cancel out all the protons, because they're gonna all be sucked up by the base, by the OH
Why'd
modes.
you add 4 waters? Cause there's 4 oxygens?
Right.
Okay.
And the way we balance oxygens
Yeah.
is to add waters to the product side. And then, where are we now? Now we're at 8 H's. But we're in basic solution. If we were in acid solution, we could stop right there and we'd have hydrogens on this side and waters on that side. But now we're in base, right? So we have to balance that out. So we add our 8 hydroxides. That's gonna make 8 waters on the reactant side.
Mhm.
But we still have the 4 waters on the product side. Yeah? But we're not done yet, because we don't have both of them on the same side because they're unequal numbers. If they were equal numbers, then we just drop them. If it was 4 and 4, both waters would drop out and we just have our hydroxides. But because we have 8 waters on this side and 4 waters on that side, we just subtract them out, and now we're left with water on the reactant side and hydroxide on the product side. Because we're only keeping track of what takes place to balance our redox equation.
Mhm.
How does the 8H plus the 8OH equal the 8H2O?
So water self-ionizes. Yeah. So if you do this 8 times, you have 8 waters.
Okay, so why did you like do the canceling on it? It's just to show that,
Yeah, to show that those two went together
okay,
to make the water. Right, it's not the.
they were like being molded.
Yeah, I could have added a, I could have put a plus sign back in.
Yeah, that makes sense.
Mhm.
Okay. Yeah, it's kind of
It
weird.
does seem like you're canceling them out, but
Yeah,
then
that's what I was-
combining.
Confusing.
Well, you know, let's not go down that path.
Okay.
Now that we know it's not the right path, let's
Let's
go
not.
down the path. Let's build the pathway to 8 H plus 8. Okay. I mean, you're right, obviously, here we go, on the
No,
fly,
no, no.
creative problem solving. Come on, all it needs is a plus, insert the things I do for you guys. Whoa, well, I don't know, kinda sketchy,
Oh, boy.
it's harder than it looks.
There we go.
Kinda making it look easy, but not really. Yeah, how's that?
That's fine.
Are we happy now?
Mhm.
Okay,
It all
control,
makes sense.
control S. Now, oh, I didn't, it's not in your notes anyway, so.
Oh.
Well, next
But
time.
next class, we'll get this highly developed flood. Oh, boy. Really?
Time's up.
I'll have to be here next semester, yes. Great, I'm understanding this.
Did you say you're understanding this?
No, I said I'm gonna have to be here next semester at the rate I'm understanding this. The opposite.
That's heartbreaking.
It's okay. This slide will make sense then.
Well, you won't get this slide, you'll have somebody else.
Oh, okay.
Yeah, so where are we? That doesn't make sense? Oh.
No, I'm following up until the last step. I really don't understand that, crossing the 4 waters and how it then
You just subtract the
takes.
4 waters, so it's pretty much subtract 4 waters on that side minus the 8 waters.
Mhm.
So it's 8 minus 4, just get 4.
But
on
why
this
are
side.
you doing that? Like,
When you have like X on one side and X on the other side.
yes,
2 things being on the same side means you can cancel them out.
I understand that.
Yeah, so if you have,
It's a
A can be
ratio.
broken up, that's technically 4H2O times 2, right?
Uh-huh.
You take out one of those 4H2Os because there's a 4H2 on the other side, that leaves you with 4 more H2Os.
Uh-huh.
It's like, you're
And
just
nothing on the other
simplifying the
side.
equation. It
Oh.
still means the same thing, you're just getting the smallest ratio.
Okay.
All Alright, anybody else wanna try to explain this?
You get here.
No,
go-
no,
go
no, what
over it-
she
go
just
over it
said,
again.
no, what she just said,
Go ahead, Nate.
Cause I was doing, no, do the next slide
that
though.
it's, oh no.
Just inviting
No, it's not, like, cause I was confused at first too, you know, my ADHD and shit. So, you got that, you can't cancel that out. Eight O's, 8 H's.
Got it.
8 H's,
Nope.
that's 8, that's 8 H's. 4 times 2 is 8, there's only 4 O's. Don't forget that 4 O's, so it's the same thing.
Ooh,
Okay.
nice.
Dumb it down, I just needed to dumb down, I was like, what
I
the
didn't
fuck is going
even,
on?
I wasn't even thinking of that way, yeah, it has to balance, right?
That was a great way.
I appreciate that.
Nice job, Nate, thank you.
Yeah.
I'm a simple creature.
I'm gonna send one of those delivery guys over to your house.
I don't do that.
Oh, no, pizza.
Oh, yeah.
Oh, no. Okay.
Alright, so, we're not doing this part. Alright.
I sell bicycles.
So if it means the same thing though, do we have to bring it to its most simple form, or could we leave it like that?
Well, if you want all the points, you get to the end.
Okay.
You could leave it however you want, you don't even have to do the problem, you can get a 0.
No, I
Basically,
just.
it's simplifying fraction, you can have the big
Right,
number,
but
but
the
it's not
fraction
as
still
pretty or
means the
worth
same
enough.
Well, you know what, it wouldn't
Well,
balance.
With math, it
Well,
means
with
the
it,
same
with it
thing.
balance also,
Okay,
Yeah.
like,
so no, cause it wouldn't balance.
We always want the smallest whole number ratio when we're describing a reaction.
Okay.
So, yes, please,
Finish.
finish.
As
Don't leave
simple
it, don't leave the reaction
Yes.
hanging.
Okay. I'll be quiet.
Alright, this is the part that we just, oh, wow, I forgot. Okay, yeah, we'll talk about this right now, and then we'll do our, nice quiz, and you guys can work in groups. 3 main ways to quantify reactions. So, we have 3 different types of ways we look to get amounts from reaction chemistry. When we make something, we want to analyze it so we know what we've made. One way is titration analysis. We use known molarity solutions. That'd be like 0.1 molar of one thing and 0.2 molar of something else, for example. Just an example. Right? We know the molarity of one, and if we use a certain volume, remember moles per liter times liters is number of moles. So if we know the number of moles of one and we have a volume of the other, we can calculate the number of moles of the second solution. M1, B1 equals M2, B2. Gravimetric analysis is a second way. That's what we're doing in lab 6, right? A measurement of weights. We weigh products to determine unknown reactant amounts. The third type is combustion analysis. We take a product and we burn it in the presence of oxygen, and we quantify carbon monoxide or carbon dioxide in water to determine unknown compounds, CNH content, and determine empirical formulas, or the relationship, the whole number relationship of elements. So with titration analysis, we add a known volume of a known molarity. So moles per liter times liters to completely react using an endpoint indicator. What's an endpoint? That's when the number of moles is equal. That's what we call the endpoint. So you have a burette and it's filled with a known solution. You dribble that into a known amount and you multiply the number of moles per liter times the volume that you used, and that gives you the number of moles. The endpoint is when the number of moles in what you're titrating or dropping drops of known molarity into a beaker of known molarity. When those 2 moles are equal, that's the endpoint, and we usually use a color indicator to do that. We did one of those in Chem 120. Step 1, liters, standard solution, times standard molarity. When we say standard, that means the one that we actually know what the number of moles is, and then we can measure the number of the amount of volume. Step 2, we do the moles of the unknown divided by liters of unknown equals the molarity of unknown. So when we look at this, That's kinda small. Well, that's kinda big.
Well,
Right. So we have a volume of standard solution needed to reach the equivalence point, or endpoint, same thing. When the number of moles are equal, that's what an endpoint is, or an equivalence point. So on the test, you would say, what equal amounts are present of reactant and product, or standard and unknown. Use molarity of the standard solution, moles. Use coefficients from balanced chemical equations. Sometimes the ratio isn't 1 to 1, right? Sometimes it's 1 to 2, sometimes it's 5 to 2. Like in problem 12 on the practice test. Remember that balanced chemical equation tells us everything we need to know between the relationship in our balanced chemical equation of products and reactants, or reactants and reactants, or products and products, or reactants and products. So that's what a titration is. We have a known amount of something, a known concentration. So remember, concentration often in chemistry is defined as moles per liter. It can be other things, but often it's moles per liter. So whenever you see a solution that says point something M, it doesn't mean IM, it means moles per liter. So we've got 0.1 moles per liter. If we have 1 liter, we have 0.1 mole. Right? If we have half a liter, we have half a point, 0.05 moles. Okay, so it's based on volume. We know moles per liter, therefore any volume, we can tell how many moles we have just by multiplying those two together. The volume times the number of moles. All right. So here's an example. Excuse me. 20 milliliters, remember, and since we're always doing things in moles per liter, I'm immediately going to convert that in my head to 0.02 liters of an iron 2 solution. So iron 2 plus is titrated. All that means is we're adding the same number of moles that are present of iron 2 with dichromate, in this case, 0.1026 dichromate, according to the balanced redox equation. So if we want to know the number of moles of dichromate, we have to know the volume of dichromate. The volume of dichromate is 12.32 milliliters. Everybody see that? Anyone not see where we get the amount of dichromate? Okay, 0.0126 moles per liter of dichromate, right, which is just almost like the example. And now we're going to add 12.32 mils, so we know we have 0.01232 liters times 0.1026 liters, or moles per liter, right, which is this number down here, right? Taking the volume that we titrated, the molarity of what we titrated, and we got the number of moles of dichromate. Now to relate that to our iron 2, we have to use our balanced chemical equation, our redox equation that we balanced, and it looks like we balanced it in acid or base. Which
Base.
one did? Try again.
Acid, dark.
Acid. How do we know?
Hydrogen 14.
Yeah, correct.
I didn't see him.
Oh, okay. Right, so that's how you know. Right. And I appreciate your being willing to volunteer an answer, because that's really how you learn. It's almost better to be wrong the first time than right, because you rarely remember when you were right. Well, unless you're me, because you're right all the time. But if you're wrong, you go, oh, I need to fix that.
Yeah.
Right, and you're aware of it. So right or wrong, if you're throwing something out there, you're going to get feedback. And anyway.
Been learned a lot in this class so far.
Yeah. Anyway, here we go. Molarity of Fe2 plus. Don't forget your stoichiometry. So we have to do the ratio, right? So we have 0.001264 moles of dichromate times 6 moles of iron from the balanced chemical equation to 1 mole of dichromate. And then we have 20 liters, right? Because we need a concentration, moles per liter. So we get 0.3792. This looks like the problem on the test. practice test, that is. So you guys see that? So get used to the idea of, if you have moles per liter times liters, we have a number of moles. Now all we have to do is compare that moles to the other reactant of interest. Gravimetric analysis example. So that was our first titration analysis. Now we have gravimetric analysis. What is the molarity of a calcium chloride solution if the addition of excess silver nitrate, silver 1 nitrate, right, to 75 mils of the solution? So again, I'm automatically going to go into liters, 0.075 liters. Produces 0.25 grams of silver chloride at 143.32 grams per mole. So we write the balanced equation. We determine the number of moles, and finally we determine the concentration of calcium chloride. Right, that's this part, calcium chloride, CaCl2. So we start with CaCl2 in solution, right, it's soluble. Do you need to get one of those?
Yeah, let me grab one.
You wanna grab another one? It's okay. Right?
I don't think there's any more, I'm gonna have to grab one. And I got
Whoa,
another one.
oh, I'm sorry. Snooze, you lose. No, that's not the right, no, that's, well, I didn't expect this many, didn't expect this many people. Right, let me know if you didn't get one and we'll print them out in lab. Okay, so calcium chloride plus 2 silver nitrate, right? We do a double displacement reaction, remember, so that we can break it down into the net ionic equations. Yeah, and because it's 2 solutions, we determine the precipitate from our solubility table, and then we know that calcium nitrate is soluble because if you only learn one thing in this class, all nitrates are soluble. That's what makes them so hard in farming communities to get them out of the water, is because nitrates are soluble. Fertilizer is nitrate.
Mhm.
So nitrate seeps into the groundwater, it's always in everything.
Yeah.
There are good filters that will remove it, however. Anyway, determine the concept, because how do they do it then? If you can't separate it by combining it with something, how can you filter it? What would be a way to filter it?
Boil it out, but that removes the water.
Okay, you could boil it. What could you do without changing the state of the liquid?
Fine mesh particle filter.
There you go. Just like we did with the COVID virus. We stopped the COVID virus, which is much smaller than a micron, by using micron-sized filters. So you do the same thing with nitrate. You use a small enough particle filter that you trap a molecule of that size, and the water passes through.
Question I probably shouldn't be asking at this point, but I still need help with it. On A, we have an aqueous, solid, and aqueous. The solid is the product, but without knowing what's aqueous and what's solid, how do you find what's the solid product?
Right.
This
Well,
is back to lab 4 stuff.
yeah, so we would go to our solubility table,
And you-
look under
you just-
chlorides and see, chlorides are usually soluble,
Yeah.
but when they're attached with silver, that's an exception. So the exceptions to always soluble are
So
insoluble.
it's non-soluble, so it's a solid.
Right.
Okay.
And that's what makes the reaction go. If this was not, right, if this stayed in solution, if this
Yeah.
was soluble as well, no reaction.
Okay.
Okay. There's no, like, I think in quantum terms, so I can miss things in that
Yeah.
way too. There's never a wrong way to go back.
Yeah.
You just go back and ask for what you need, we put it in there, no harm, no foul.
So then, jumping to net ionic, if all 4 are aqueous, would that make all of them observers? Because
Yeah, no reaction.
Yeah.
Right.
Okay.
Yeah, so what it doesn't change, it's a observer or a spectator, right? I don't know why we have to use the word spectator, but
Yeah.
apparently. So,
Okay. Thank you.
you're welcome. So, that's that, and that's the end of our slideshow, so let's pass out I hope I have enough of these. That'd be weird. And then, of course, as always, with nice quizzes, you have the rest of the period, and then it's due tonight, SO4, 2 minus aqueous. And then, so that's the complete, and then zinc solid plus copper aqueous yields zinc aqueous 2+, plus, and this is copper 2+, plus copper solid. Yeah? So this is, because they all change, right? They change states. If they change states, they're not the same as they were on the reactant side. So they have to be included. So one goes from solid to liquid, the other one goes from liquid to solid. Little nuance there.
You want us to put the charges like that, or just?
Yeah, you always include charges for ions.
Yeah.
Karen, I want glasses. Yes.